Are you ready for sustainable tire production? Difficult times require an analysis of processes and consequently a development of new strategies, so you can get back into action. HF, sent for future demands in tire production. Join us for iTech 2020 Virtual Edition on September 10th, 12 p.m.
Hello everyone, I'm Bruce Meyer, editor of Rubber and Plastics News. Welcome to the International Tire Exhibition and Conference organized by Rubber and Plastics News. We're certain you'll enjoy the variety of speakers and panel discussions offered throughout the conference. Our speaker today is John Dick, who has more than 45 years of experience in the rubber industry. He was with BF Goodrich and then Uniroyal Goodrich Tire Company as a section manager and development scientist in R&D until 1991. John then joined Monsanto's Rubber Instruments Group, which is now Alpha Technologies, as a senior scientist in applications until 2016. He is now a brand ambassador for Alpha Technologies. John has authored more than 80 journal and magazine publications, including 5 books on rubber technology. He consults, gives technical papers, and has given seminars in more than 40 countries. He also now serves as technical editor of Rubber and Plastics News. Let me now turn the discussion over to John.
My presentation today is titled The Use of the New ASTM D7723 for Measuring Dispersion via the Computerized Reflective Microscope Method. Next slide. ASTM D7723 is a relatively new procedure. It is built on the Dispersion. The Dispersion has been used in the industry for quite a while now, and we're standardizing the method in which we use the data and how we record the data and make our measurements. Next slide. The Dispersion works on the principle of having light coming in on the rubber sample at a 30-degree angle, and that light, which reflects into the lens of the microscope, is recorded as white area, and as opposed to black. And by using special equations, we can calculate the percent dispersion with various algorithms that we've worked out. Next slide. The way this works is you have a beam of light that hits the surface of the specimen, as shown here on the next slide, and it reflects off and does not enter the lens of the microscope, so that's recorded as black area. On the other hand, on the next slide, you can see, in the slide after that, you can see that the light actually reflects the agglomerate that is not dispersed in the rubber. This is the agglomeration, which is not broken up yet from mixing, and it's recorded as white area. On the next slide, we're really talking about a star field, to use an astronomy term. And the amount of white area you have shows undispersed agglomerates, and that indicates a lower state of mix. But as you put more work history into this, these agglomerates break up, and that becomes, what was white area becomes dark area or black area. On the next slide, you can see the 2 equations we commonly use in the standard. One is called percent D dispersion. This is when we already know what the loading level of the carbon black is in the compound. This is already known, so we can substitute the percent L in that equation. But quite a while ago, people prefer to use another calculation called the %Z dispersion. The %Z dispersion doesn't require you to know what the loading level of the carbon black is in the compound. Instead, we substitute 35, which is most representative, and this has worked out well in the industry, so much that most people want to actually calculate %Z rather than %D in their studies. Next slide, please. So the way we measure this is we have a special apparatus to using a very fresh razor blade. We automatically cut into the sample very quickly, and we try not to smear. To avoid smearing, we have a 10% stretch on it to keep the rubber from smearing, because that will interfere with our measurements. So this works very effectively for uncured rubber. So on the next slide after that, this is using the cured specimen. The cured specimen doesn't have the same problem with smearing, and some people commonly make their measurements off cured specimens, but it's not required. Lots of good results also come from the uncured specimens. Next slide. This is just demonstrating how that works. And then the next slide is more detail on that. Okay, then the next slide, we see the new ASTM D7723 suggested that the standard conditions for both the carbon black and the silica dispersion measurement should be as shown here. After much discussion and work that we did in the lab, we finally came up with a decision to recommend that white area threshold on the computer should be set for 23 micrometers. Also, it was agreed that we should commonly use an exposure time in the camera of 40 milliseconds. Thirdly, we agreed that the position of the illumination should be at the top. And lastly, we agreed that the color channel for analysis should be blue. So by running these conditions, we find that the repeatability and reproducibility and accuracy are much enhanced. So this is looking at how we compare to a newer method that we've developed in ASTM for dispersion, and that's known as ASTM D8059. In 8059, we have a situation where we use the pain effect to measure the state of mix, exactly what the quality of mix is. And this has been used for quite a while now, and is particularly popular for silica dispersion. So on the next slide, we see that measuring carbon black incorporation for deagglomeration, that was the goal of this study. This part of the study involved measuring rheologically the effects of carbon black incorporation and deagglomeration at different stages of the Banbury mixing process. In this design of experiment, each raw elastomer compound was mixed with exactly 35% by volume of N330 carbon black in this study. On the next slide, during the BR Banbury mixing process, 20-gram aliquot samples were taken from the mixer after 3, 3.5, 4.5, 5.5, 6.5, and 7.5 minute intervals. Each of these samples were tested by the ASTM D7723 procedure for percent Z dispersion with the dispergrator, and on the RPA by the new ASTM D8059 that we've just talked about. And we're using the pain effect to measure what the dispersion is. On the next slide, the reported, in the literature, you see reported the carbon black affinity for different elastomers. Usually different rubbers in a blend are not perfectly soluble with each other, so they will commonly establish continuous and discontinuous phases. Therefore, typically, the available carbon black is attracted more to either the continuous or the discontinuous rubber phase, depending on which one dominates. Typically, carbon black affinity for different elastomers is ranked as we show below, where you have the greatest affinity for carbon black actually with polybutadiene. And SBR is also very much attracts carbon black. They're very carbon black friendly. Neoprene is not quite as much. Nitrile rubber is even less. And natural rubber also has some problems with that. Then you get into EPDM, which is almost carbon black phobic in some ways. And then you get into regular butyl rubber, which is the most unfriendly to carbon black. So on the next slide, we're going to talk about our studies with SBR base. On the next slide, you'll see that ASTM D7723 for measuring the percent Z dispersion is plotted on the y-axis versus the work history we've applied in this special study with SBR on the x-axis. And you can see a curve that kind of reflects the law of diminishing returns, where it marginally takes more and more work history to get a marginal improvement in the dispersion. We've seen this before, and it's typical of this particular situation. But using a curvilinear regression analysis, we can get an R square equal to about 97% predicted, which is quite good. So the percent Z dispersion worked pretty well here. On the next slide, you will see that using the pain effect method with ASTM D8059, you can see that when you look at the pain effect curve itself, which is a result of a strain sweep, at the very low strain of only 0.05% strain, very low strain indeed, you're able to relate to the state of mix. In other words, all these curves are forced downward with more work history because they're breaking up the filler network in the mixing process. So it's a good effective way of measuring what your state of mix is. On the next slide, we can see the actual plot of the G prime at very low strain with the work history, and we get an excellent correlation coefficient of R squared equal to 0.98. So it's 98% predicted with very little error. On the next slide is a natural rubber study that we did. We're using a natural rubber base. As we can see on the next slide after that, we can see the percent Z dispersion that occurs as you increase the mixing time. You see the percent Z dispersion increases rather quickly with natural rubber because it has quite a bit of torque and can really disrupt and break up that filler network, and that results in good dispersion if you've got enough torque to do that, which we do. So this is what that the Z number is giving you a R square equal to 99%, which is very good. The next slide, we see what the pain effect looks like with natural rubber. As you put more work history into it, you lower that pain effect curve, as you can see here. On the next slide, you can see the correlation, excellent correlation with the initial G prime, which after given work history, it's lowered quite a bit. And the R square on this comes out to be 96% predictive. So that's good. Then looking on the next slide, we're studying BR rubber. BR is one of the big three commodity rubbers used in the tire industry, of course. And BR, though, is typically used with another elastomer. It's blended either with natural rubber or SBR. It's unusual to use it by itself, which we're doing here. On the next slide, you can see exactly what the Z dispersion shows as you increase the mixing time, and you get a fairly good R square of about 85%, which explains 85% of the variation, which is good. It's not as good as what we got with the natural rubber and the SBR, but it's acceptable. Then look on the next slide. We use the alternate method of measuring dispersion, the pain effect method, ASTM D7723. And in using that, we see that it is affected by different work histories. And looking on the next slide, you can see there is a sort of decent correlation with the initial G prime for the low strain versus the work history. You get an R square equal to about 75%. There are some problems with BR. And in fact, this is more of an academic exercise with BR, because BR, like we said, is always used in a blend. But if you were to use it by itself, then there aren't many tire compounds that would use only BR. This is the kind of result you would get. Okay, on next slide, we're talking about bromobutyl. Bromobutyl is polar enough to give you pretty good results in this study. On the next slide, you'll see that the percent Z dispersion for the bromobutyl is very good. Well, we got a 97% prediction for the R square, which is very good. Looking at the next slide, you will see that looking at the effect on the pain effect that you're seeing, the initial G prime is forced downward, like you have seen with other examples. And looking at the next slide, you can see that the G prime for the pain effect predicts very good correlation, and R square equal to 95%, which is very good. 95% explained. So that's very good, actually. In fact, on the next slide, you can see these two parameters, one from ASTM D7723, the other from ASTM D8059, and they correlate beautifully. You can see the correlation for these two separate methods, one on the x-axis and the other on the y-axis, is giving you an R square equal to 98%, which is very good. On the next slide, we look at what happens when we use regular butyl instead of bromobutyl. And just a little bit of halogenation makes a whale of a difference, because when you look at regular butyl, it doesn't have the same carbon black friendliness that you got with the bromobutyl. So when you're looking at the percent Z dispersion with a Dispersion method, you can still predict where the state of mix is from this, even though the R square is only about 73%, but it's usable. Looking on the next slide, however, you can see, oops, I think okay. On the next slide, you will see that there isn't that much difference in the compatibility. It's equally incompatible. So it looks like the same curve, actually. So now going to the next slide, you'll see that you get more of a shotgun effect here. The R square indicates there is no correlation. So this is what happens with regular butyl. It doesn't have very good compatibility with carbon black, and that's why you get this shotgun pattern. On the next slide, with EPDM, EPDM is sort of like butyl, regular butyl, in that it's not all that compatible with carbon black either. So on the next slide, you see with the Dispersion method, the ASTM D7723, you get some correlation with state of mix. However, on the slide after that, you see that you get pretty much the same curve on the paint effect side, because the more work history you put into it doesn't really move the paint effect curve that much. So in the next slide, you'll see that you get another shotgun effect on pattern, and you have a very poor R square, which you would predict. So next slide, we talk about our work with SBR and getting good dispersion with silica. Now, in this study, we used TESPT, which is an organosilane, which makes silica suddenly friendly with SBR. So it is possible to get good dispersion with SBR if you're using an organosilane. Also, this TESPT came from what we call X50, which X50 contains both TESPT and carbon black. So by using the X50, you also add a small amount of carbon black, enough to tint the color black, so that you can use Dispersion for making these measurements with silica, because it has to be a black background to measure the dispersion of silica particles with the Dispersion. Next slide. On the next slide, you see that the percent Z dispersion is quite good, actually. With that tinting of the background, you're able to quite effectively use the Dispersion, in this case, with the organosilane. And you've got a pretty good correlation. R square is equal to 0.966, which is very good prediction. Follows work history to the letter. Next slide, we see what success we had with the paint effect method with ASTM D8059, and we get the spreading out of the paint effect curves as we would expect with added work history. So on the next slide, when we look at what that does for our G prime measurement at very low strain, we get a very nice correlation here as well, R square equaling 0.95, which is very good. On the next slide, after that, this is a summary of the coefficients of variation, the R squares, in other words, for the two methods we were talking about for the silica dispersion. So both are very respectable. So both methods worked quite effectively with silica. And there's some evidence that the paint effect method is actually better than the microscopic method, in that it measures the paint effect and the effects that has on the compound, and that evidence is that it's very effective at measuring silica dispersion specifically. So lots of people are using this method now for measuring silica dispersion. On the next slide, you can see what happens when we plot the ASTM D7723 parameter, the Z dispersion on the y-axis against the x-axis, which has the G prime pain effect property at very low strain. And you see what's a little bit unusual is there's the curvature to this, which can be explained by the fact that earlier studies that we've done show that the silica has a much longer incorporation stage than it does have in the dispersion of the silica. So this longer incorporation stage causes this curvature. Like on the next slide, you will see that what I'm talking about, where the G prime in the incorporation phase actually goes up with mixing time, but then it starts going down with dispersion time. So what this is saying is that if you're serious about measuring the dispersion of silica with the Dispergrader and with the pain effect method, especially with the pain effect method, you want to start taking your samples later when it's in a dispersive area rather than when it's in the incorporation area. On the next slide, we study the SBR tread compound using solution SBR for low rolling resistance. This tread formulation has about 80 parts silica and it's used in lots of models. It's the one that's published in the next slide. It's the one published in ISO 5794. And this is quite effective and it's very representative of what's used there today in the industry. So we use this particular tread formulation for our studies that we're going to discuss. On the next slide, you can see how the correlation came out for the percent Z dispersion of the silica dispersion in this particular tread compound. And it came out very good, I think. The R square came out to be 0.865, which is very good. And so that worked quite well. And then on the next slide, you can see the pain effect method where added work history causes a suppression of the pain effect curve, as you see here. So on the next slide, you see that plotting the G prime versus mixing time, you see there's a little bit of scatter initially. The reason there's scatter initially is because the incorporation phase that I was talking about. If you're, I think when you're at 4 minutes, you're still in something of the incorporation phase and not the dispersive phase. Now, if you go to the next slide, after that, you see that the correlation gets much better and you're at 94% explained when you remove that 4-minute mixing time and just start with 5 minutes, which indicates that if you're using this pain effect method for measuring dispersion, you might want to hold off on measuring it while it's still in its incorporation phase and wait till you get into the dispersion phase before you start taking your measurements. On the next slide, you see a direct comparison of the coefficients of variation for the ASTM D8059 method, which is a pain effect method, which gave the highest result. Maybe that explains why it's used so much in this area, versus the Dispergrader method, which is not bad, but not as good as the pain effect method. The Dispergrader method gave 0.865. So the conclusions that we've reached here are shown here. First of all, ASTM D8059 pain effect method and the ASTM D7723 %Z dispersion with the Dispergrader are both effective at measuring state of mix that's work history, and a degree of carbon black or silica dispersion in compounds based on general purpose elastomers. Our second conclusion is that ASTM D8059 paint effect method is compromised somewhat by compounds based solely on regular butyl, which doesn't happen too much in the tire industry, or EPDM, which also doesn't happen too often in the tire industry, because these two polymers possess poor affinity for carbon black compared to the other elastomers. And lastly, the predictive power of the percent Z dispersion test, that's ASTM D7723, for final state of mix was significantly improved when the average of two samples were used. That is the central limit theorem. That improved it quite a bit. So if you take two samples instead of one, you're much better off, and you'll get beautiful correlations. So if you have any questions on any of this, you can reach me or send an email to me at john@rubberchemist.com. That's john@rubberchemist.com. And thank you very much.
Thanks for an excellent presentation, John. I would also like to thank our audience for attending this session. And thank you to our sponsors for supporting iTech Virtual 2020. If you want to revisit this session or any others from the conference, they will be available on Rubber and Plastics News website, rubbernews.com, after the event is completed. If you would like to purchase papers from this and other sessions of iTech, visit itech-tireshow.com to do so. And don't forget that you can connect with your colleagues here through the virtual networking program, which can be found on the left-hand side of your screen. Simply click the Meet icon just to start connecting with fellow iTech attendees. Thanks for joining us today.